Another way we can look at solving differential equations is by using power series. But before we get into how we can use a power series to solve differential equations, we want to take a quick review from calculus of what is a power series. So let's look at these power series. Basically, a power series centered at A is the sum, as n goes from 0 to infinity, of some constant times x minus a raised to the n power, which means we can take that bottom number of 0 and plug it in to get c sub 0 times x minus a to the 0 is 1, plus plug the number 1 in and we get c sub 1 times x minus a to the first power, plus plug 2 in, c sub 2 times x minus a to the second power, plus and so on with the third constant to the third power, fourth constant times to the fourth power, and so on and so forth. Now, usually in this course, we're going to be interested in power series that are centered at the origin or at 0. Which is nice because when we plug 0 in for all the a's, the power series simplifies a little bit to c sub n times x to the n power. So it's just a constant plus a constant times x plus another constant times x squared, and so on and so forth. In other words, it's a polynomial. Well, with these power series, we're often interested in whether or not they converge or diverge. And so what we found is we can calculate what's called the interval of convergence. Or the range of numbers for x for which this series will converge. We called this the ratio test in calculus, which said we could take the limit as n goes to infinity of the next term, in other words, c sub n plus 1 times x minus a to the n plus 1, and remember a is usually 0, but not always, divided by the current term, c sub n times x minus a to the n power. Well, what's nice about this is we can simplify by reducing the x minus a's to the n plus 1 minus n means it's just going to be x minus a, which is not dependent on our variable n, so that can come out. So we get x minus a times the limit as n goes to infinity of whatever the next constant is divided by the current constant. And we would say that is equal to RL. And it turns out that this series, this power series, converges if L is less than 1. If that limit is less than 1, it will ultimately converge to some finite value. So let's see if we can take a look at the power series. This one's centered at 3, as n goes from 1 to infinity of x minus 3 to the n over 2 to the n times n. And we want to know, when is this power series going to converge? Well, to calculate that, we can take the limit as n goes to infinity of the next term, which is x minus 3 to the n plus 1 over 2 to the n plus 1 times n plus 1, all over the current term, which is x minus 3 to the n over 2 to the n times n. Well, we can simplify this division by a fraction by multiplying by the reciprocal. So we've got x minus 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 times the reciprocal, which is 2 to the n times n over x minus 3 to the n. And if we look at the x minus 3 to the n's, we can divide out n of them. And if we look at the 2's, we can divide out n of them. And so I can pull out the x minus 3 and the 2, because those are all constants. And we're just left with the limit as n goes to infinity of n over n plus 1. And we know from calculus that that limit is going to equal 1 because the coefficients are 1. And so what we really have is the absolute value of x minus 3 divided by 2. And since 2 is always positive, we can just pull the 2 out of the absolute value. Well, we want to know when this converges. Well, if it's true that this only converges if this limit is less than 1, then what we can do is we can say that the absolute value of x minus 3 over 2 is less than 1 and solve this resulting equation. Multiplying by 2 tells us the absolute value of x minus 3 is less than 2. Then we know if the absolute value is less than 2, the x minus 3 must be between 2 and negative 2. And so we can add 3 to both sides. Actually, all three parts. Adding 3 gives us 1 is less than x, which is less than 5. The problem with this range is we don't know what happens at exactly 1 and exactly 5. So what we're going to do is we're going to plug them back into the original expression to see what happens if x equals 1 and if x equals 5, to see if we can say it equals 5 or is just strictly less than. Well, if x equals 1, our series becomes the sum as n goes from 1 to infinity of 1 minus 3 is negative 2 to the n over 2 to the n times n, which is the sum as n goes from 1 to infinity of negative 1 to the n over n, because the 2's are dividing out. And you might recognize this as the alternating harmonic. Which we should remember the alternating harmonic converges. So we can add an or equals to on the 1 because x does converge when it's equal to 1. So what happens at 5? Plug a 5 in and we get the sum as n goes from 1 to infinity of 5 minus 3 is 2 to the n over 2 to the n times n, which the 2 to the n's can reduce out, and we get 1 over n, and that's just the regular harmonic series. And the integral test will tell you really quickly that diverges. So we cannot be equal to 5, so it's going to be strictly less than 5, but greater than or equal to 1. This is the interval of convergence. We also might be asked about the radius of convergence. In other words, how far from the center of 3 does this series converge? Well, that's going to come from where the absolute value is less than 2. So I know the radius of convergence here is going to be equal to 2. All right, that's a quick review of power series and how power series work. One thing we're going to be interested in doing with our series as we work with our differential equations is we're going to often be interested in if we can shift the index on a series. And the idea here is that we can change the index, that's the n equals 0 to infinity part. We can change that n equals to a different number as long as the expression and the index go opposite direction. The index and the expression go opposite directions. And here's what I mean by that. If we've got the sum as n goes from 2 to infinity of n times n minus 1 times c sub n x to the n minus 2, and let's say we wanted to shift this index so it started at 0 instead of 2. Well, the index then would be subtracting 2. So the expression has to go the opposite direction. Every time we see an n, we're going to go the opposite direction, and we're going to add 2 to all of these n's. And when we do, we'll get the sum as n goes from 0 to infinity of what's now n plus 2 times n plus 1 times c sub n plus 2 times x to the n plus 0. Both of these expressions represent the same thing. We've just shifted the starting point, or the index. For example, if we were to start to build these series, the blue series starts at 2. So if I plug 2 in, we have 2 times 2 minus 1, which is 1, times c sub 2, times x to the 2 minus 2, which is 0. Plus, we would count up and plug 3 in next. N is 3. Times 3 minus 1 is 2, c sub 3, x to the 3 minus 2, which is 1, and the series would continue. Notice that's going to be exactly the same thing as the green series. If we start with 0 now at the bottom, plugging 0 in, 0 plus 2 is 2, 0 plus 1 is 1, c sub 0 plus 2 is 2, x to the 0, plus, next we plug 1 in. 1 plus 2 is 3. 1 plus 1 is 2. C sub 1 plus 2 is 3. X to our 1 plus, and as you can see, we are ending up building the exact same series. But what we've done is we've shifted the starting point, or the index, on our series. That's going to be a really helpful trick as we move forward working with power series. Another thing we can do is we can add series together by matching exponents, then indexes. Here's what I mean by that. We might have the series n going from 2 to infinity of n times n minus 1 c sub n x to the n minus 2 minus the sum as n goes from 0 to infinity of c sub n x to the n plus 1. And we want to combine these together to form a single series. We're also going to decide we want to start our series at 0. Well, the first thing we want to do is make sure the exponents match. Right now, if I plug in the first index of 2, we end up with x to the 2 minus 2, which is 0. On the second section, if we plug in 0, we end up with x to the 0 plus 1, which is 1. Those are not matching indices or exponents on x, which means they cannot be combined as like terms, unless we pull off the first term. And that's what we're going to do here. We're going to pull off the n equals 2 term out of the series. When we pull that out, plugging 2 in, we have 2 times n minus 1 is 1, times c sub 2, x to the 2 minus 2. Now with that pulled off, we've got the sum as n goes from 3 to infinity. N times n minus 1, c sub n, x to the n minus 2, minus the sum as n goes from 0 to infinity of c sub n, x to the n plus 1. Now you notice if we were to plug in the bottom index into each individual expression, both x's would be a power of 1. Now to combine these series together into a single series, we need to agree on a common index that we're going to go for. We can either drop the 3 down to 0, and so they all match at n equals 0. Or we could pull the 0 up to 3 and make them all match at n equals 3. Or we could make the exponents on our variable match. That's what we're going to do this time. We're going to make these all have x to the n when we're done. So this middle section, the first series, to make it x to the n, we need to add 2 to the exponent. So we're going to add 2 to all the n's, which means the index needs to subtract 2. On the last series, to make it x to the n, we need to subtract 1 from the exponent. So on the index, we'll do the opposite, and we'll add 1. Now when we simplify, the first term just becomes 2c sub 2 plus, the sum, and now you notice both sums start with an index of 1 going to infinity. Another thing that both sums have is they both have an x to the n power now. I'm going to go ahead and factor out that x to the n now. When I do, I'm left with n plus 2 times n plus 1 c sub n plus 2 minus c sub n minus 1. And now we've combined those two sums together as a single sum. This strategy is going to be helpful to us when we get to working with solving differential equations using power series. But for now, it's important that you get a chance to practice reviewing power series, finding their interval and radius of convergence, and also shifting the index so that we can add series by first matching the exponents and then matching the index. Take a look at practicing, and good luck.